Hello everyone. We start this meeting now, but since no one has joined, we'll uh, wait for some time. I think it's 15th of August. Let's say no one joined. Hello. Yeah. So since nobody is here, I'll just record this tutorial on my own, and I will post it on the YouTube for you guys to follow it later when you are free. Okay. So I'll just share my screen now, and I'll start presenting the work. I hope my screen is visible, and let me do the slideshow. Okay. So this is deep learning for computer vision, and the live session 3. And so in the last week, we started to, let me open the notebook as well. Okay, so I will get a page. Yeah, so it is with 3, it is feature extraction. Feature matching, sorry. Feature matching. So what we learned earlier is that given an image, so the goal was to sort of take the image and sort of figure out what are the features uh, in the image. Like let's say there was there is the image of a cat, and okay, and so initially we sort of tried to get the edge of it. So after the edge, we try to extract features such as curves, and then so edge can be two things, vertical and horizontal. Then edge, curves, then sharpness, and many more things like so. Edges, curves, and sharpness, and things like that. And so what happens is that we can use this feature for our learning. Also, we can use this feature to intertwine with each other to give us complex features, which we cannot name, which you cannot name, but these will be the features which are sort of linear or non-linear combination of the original features that we can name, such as edges and curves. So this is that we will do in the deep learning, but initially we were just finding features, and the task was, so now the task is to match feature. So let's say there are two images, and this two image is taken from the same location but from a different angle, and a lot of point in this two images uh, uh, are similar and are same actually, and the task is that how to merge these two images. So let's say I have an image of the same place, of the left side and of the right side, and how do I merge this image? And one of the practical application of this thing is that of the panoramic picture that we capture generally, like let's say we are trying to take a shot of a very large
horizontal area. And so let's say when to do that, and what we do is that we sort of move the camera in the horizontal axis slowly, so that the camera could be able to capture the entire thing, and and give us an image. But what happens is that in this sort of setting, uh, it doesn't really like so the task is to now merge these two images. So what to do is that the task is that how to match key points in two different images. So one way is that find the key points in this image, find the key point in that image, and match them. And if these key points are similar in this two same into two images, we can just overlap those part of the key image in the second image, so that we'll get a continuous image and a big image. So if you have followed the lectures, you must have seen there are a lot of method to do that. So one method was dense registration through optical flow, and the second method was wide baseline spatial matching, and the final method, which was the state of the art, was ransack algorithm. So dense registration uh, and dense registration through optical flow was the point where we sort of tried to find all the uh, all the give me 1 second. Yeah. What happens is that, so we take two images and we find all the key points in the image one, we find all the key points in the image two. We sort of try to then match these key points in these two images. But the problem with this would be that so there will be some objects which will not be in the image one, and there will be some object which will not be in the image two. I mean the target image, source image and target image. So in that case, uh, the algorithm will match to rubbish points in the image number two as to image number one. So that doesn't make sense. And also, if the points are uh, outliers, so this dense registration of through optical flow and wide baseline spatial matching cannot handle them. And this is the reason we sort of start looking into methods such as ransack. And the full form of ransack is a random sample consensus. Okay. So I'll show you how this exactly this ransom algorithm work. And yeah, give me 1 second. So so the way ransack algorithm work is that, let's say this is the plot that we're making. uh yeah Let's say this is the plot of the points that are matched from image number one to image number two. Give me 1 second. Yeah. So, so the way Ramsay was proposed is that yeah, the way it worked is that uh, let's say there is a point in the original image. We want to map this point to another point in the final image. So we want to make sure that this point is equals to this point in the final image, and we sort of uh, try to, so, and this image, this is image I, and this is I dash, and I dash can be a rotation or translation or any other operation of the original image I. Okay. And interesting thing is that it can be a linear combination of all these things as well. Okay. This can be this image I dash can be first translated to through translated in the direction of x, then rotated so let's say by theta angle. So this can be the case as well, uh, where the image I dash is a linear combination of all the associated transformation that can happen. So so if I we know that I if I dash is belongs to R square, that is a matrix, and I also belong to R, that is a matrix, we can say that I so, and since it's a linear transformation, we can say that I into A equals to I dash. So by saying I into A equals to I dash, we claim here that this A is a matrix that contain all the linear transformation that is like there in this uh, initial image final image. And if we can solve this, we can solve the problem that why like this rotation and translation is happening. Like I mean, we can say finally say that what points in the source image one is corresponds to what points in the source image two. So this is interesting that we sort of said so, and we assume that this is a linear combination, and at some point it might happen. What might happen is that this transformation might not be linear. Sometimes it happens is that the transformation might not be linear, and we end up matching it wrongly, matching it wrong. Okay. So and also there's a case that might be some outliers. Okay. So if you recall this equation is a uh, linear equation, and to solve linear equation, what you need to do is that we need to, so this is I matrix and this will be A matrix and this will be I dash matrix. Yes. Okay. And this is not a matrix actually. This is a row. This is a column vector. I is a column vector. So I'll just yeah. So I is a column vector now. So because it will contain this value x, y, and one here, x dash, y dash, and one. Okay. This will contain all the values. And if you recall from your yeah, if you recall, you can definitely see that. If you recall, you can definitely see that uh, uh, yeah, if you recall, if you can definitely see that this is not the this is the way we solve the least square problem, which we solve by regression. And what we do is that for that we sort of first plot all our XY combinations. Draw a bit more here. We plot all our XY combinations. Then we sort of try to fit a line in here. Okay. So this is the case where what we do when we sort of try to fit a line inside this uh, inside our data points. But the problem with this is that if there is an outlier, the line would not be a good approximation of the data points. Okay, this line will not be a good approximation of the data points. So since the line is not a good approximation of the data points, we need to find a way. So the problem is that let's say this is a pre-dimensional one. Let me draw it again. Let me draw it again. Okay, so let's say these are the points. Okay, and there is some outliers here. Okay, and now this line will be changed. So let's remove these pips. Yeah, now this line, this was the line earlier. Now this line will be changed to something like this because of this attraction from this point. Okay, so these are the outliers, and we need to work on that. We need to say that there are the outliers, and we do not need the solution of our problem get influenced by the outliers, because if it gets influenced by the outliers, we'll not be able to match points between two images accurately. And if we cannot do that, we'll not be able to overlap two images accurately. What we can do is that we'll do the overlapping and it will not be good. So to do that, we need to bypass these outliers. We need to say that. So how these outliers came in the first place? So let's say we're trying to merge a scenery, and there are two images, and you stood here and took two images, one in this angle and one in this angle, and you captured half of the mountain here and half of the mountain there, and but here also you captured a house, and here you capture a tree as well. Okay, even if some points here and here are matching, based on it you are going to overlap it, there will be some matching from this point to this point as well. So this gave rise to this outlier, and we need to discard this outlier, and we need to tell the algorithm that you should not be influenced by the outlier, and keep the line where maximum number of points are overlapping. Okay, so this was the case. And to do that, this let me yeah so to do that, the algorithm that I'm going to discuss is the ransack algorithm. So this is the why previous method failed. They couldn't handle the outlier. So you can see here's the outlier, and for this point, this entire line is off the track. If it had if it were like drawn in this shape, it would have been better for all the points, not for this point. But now it is off the track. It is not good for any point, just good for just one point. Okay. So there is the algorithm. So before going to the algorithm, I'll just try to tell it by describing it how this algorithm works. Give me a minute. So what happens is that so uh, so let's say so X is the data, like the correspondences between two images. The what do you say? Uh, the key points in image one that is matched to key points in image two, and then let's n is the minimum number of sample to fit a model. So we know that. So to solve a equation in 4 variable, we need at least 5 variable. Uh, uh, we need at least 5 equations to solve that, right? So similarly, we need minimum number of point to fit a model to a to solve a particular equation. Let S is a function is a score function of a sample X given the model parameter theta. So if we give the model parameter theta, let's say the score that we're getting is X. And so basically the score is just RMSC, I guess. Like so like if you draw a line like this, the distance to this point would be the score. So the more the distance, the less should be the score. And let's say this distance is t. What you do is that we get a norm of t, basically the second, and which is the Euclidean distance. And the more the distance, the less is the score. And uh, if the score is higher, we want the line to fit much more into this point. So it is inversely proportional. So we get a score function, for example, X given the model parameter theta. So since it is a regression problem and this is a line, so the model parameters would be, so theta would be just the slope and the intercept equals to MC. Okay, so yeah. So this is the Ransack algorithm that I'm discussing. And so once the score is fixed, now we need to just look at this loop, for loop, or like just a loop statement. So what you do is that draw n state, draw n samples, that is h belongs to x, like the set, and from x, so x is the entire data set, and fit the model H to compute the parameter theta. Let's say we just fit a random line to there. And see, and the second is a verification step, where you see if the data are consistent with the hypothesis, and compute the score. And if the score is greater than the original one, we say that uh, this is uh, uh, this is the weight score, and we will solve this parameter. We will just store these parameters, and we'll just store the scores. And if it is not, the score is not more than that, we sort of try to repeat it, repeat the formula. And since we're drawing this randomly, this makes it like the sampling from the this makes it sampling from the distribution, and it makes it random. And since we're sampling things randomly, and they tend to increase the score of uh, the hypothesis. Okay, so I'll just describe what I said in a picture format. Give me a minute. Okay. Okay. So let's say okay. So what happens is that so we'll first let me do it in blue. Better. So what happens is that you pick 2 points. So there'll be point, lots of pointer here. Let me draw the points. Okay, so you pick 2 points. So this point and this point. Then you draw a line first. Okay, this is sampling 2 points and hitting a line, and then draw a little neighborhood around that. Okay, and sort of try to count how many points that came in the neighborhood when you draw that. So there will be quite a few points that will come in the neighborhood in this way. So just count that. Okay, just count that to see how many points are there in the neighborhood, and how so that will be the score. Okay, so in this Francis algorithm, that will be the score, and that is done. And then again choose 2 more point. So let's say this point and this point. You choose that, you draw another line. But excuse me, yeah. So draw another line. You draw another neighborhood as well. Okay, this is your neighborhood, and you again count them. So this is, let's say, score. This, let's say, score 1, and the parameter theta 1. So theta 1 would be now m1 p1. Okay. Okay, and this is m1 and c1, and let's say this is the line number 2 with score s2 and theta 2. Theta 2 are the parameters, and which is again m2 and c2. Okay, so now we have now we have the line and the score and the parameters with us, and now we can say that we are now you can say that we are having this now you can say that, so if let's say s2 is greater than s1, so what we will do, so it is this corresponding line slide. This line, if s star is greater than s, store the parameter as well as the score. So we will be storing, so we will store the score equals to s2 and theta equals to theta 2. Okay, this we did. So, and let's say in the third iteration we chose a point here. Let me just circle there so that we can see what the point that we chose earlier. And let's say I chose the second point here. Okay, and let's just let's just draw a line between this two point. It will go like this. No, it will go like this, and if we build a neighborhood around it, okay, if we build a neighborhood around it, we can see that this has the maximum number of scores. Okay, number of points in the neighborhood, and let's say this has a score of score 3 and parameter 3, that is equals to m3 and c3, and you can see that we can clearly see that this has maximum number of maximum number of um, uh, slope and uh, maximum this is the maximum number of points in the neighborhood. That's why it has the maximum score as well as the maximum uh, maximum score, and so that's why we're storing the score and the parameters. And if you do like that, if you just repeat and do this iteration for a fixed number of fixed number of times, uh, 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 yeah, so if we do that fixed number of times, realize that, and since we're storing the best one, we realize that the line would be lying somewhere like this, here, here, or like here. So this will be for the time being. We can put this as our best line that we have got, and this is the line should lie, and this would be the correspondences between those two images. Coming to the application, so Dancek has a lot of application in today's world, such as like rotating the image. So we can rotate the image, and still we can preserve all these things that is there in the original image. Then second is homography. So homography is stitching images, different images of the same place, different non-overlapping, like different somewhat overlapping images of the same place taken from the four different angles. These were like overlapping, these parts were overlapping. What they did is that they used the Ransom algorithm to merge these two images and get a bigger image. So this is like homography, and to do that we do that. And but the problem came when the image is so the object is the same, but the type of object is the same, but the exact object is different. So if you see here, it's a different instance of the same object. So object, what we say in the computer science, is a class of thing have a different with the same characteristics, and each instance will have a different sort of tone to it. So speaking about this helicopter in the left and this helicopter in the right, so we can as humans say that these are these two are the same thing, these both are the helicopters. But uh, as a computer, it's very hard to explain to the computer that these two are the same object, but just from a different brand or just from a different manufacturer who manufactured it differently. That's why the safe size and the style of the construction of the object is different. This was the problem that people faced when they tried to uh, deal with this helicopter. But then we come across this two algorithm, out of which one we will be discussing today. So these two algorithms really give me a second. Where's the okay? Okay, so then this two algorithm, which came as a life saving for us, and we use this two algorithm to match different instances of the same image. We'll discuss about the bag of words model now, and we'll see how the bag of words model helped us like identify two different instances of the same object as the same thing. So what we do is that uh, bag of word is something that that was taken from the text or the NLP domain, where a sentence or a entire paragraph or book will be broken down into small words, and we put it inside a bag, and all the and it will first the words will be cleaned, because let's say the one word is see, and the second word is seen, and so seen and see at the same word with different var format. One is simple present, one is simple past. So we don't want to count those two words as a different word. So what we do is that we clean them, and after cleaning them, we put all the unique words in an entire corpus. Corpus is a collection of text uh, to uh, to a place, and we call that a bag of word model. Similarly, what we do is that sentences have words. Sentences, or like big paragraphs or books have words, which are the smallest unit. But if you see in images, the smallest unit is the pixel, and we cannot just break pixel to a pixel level, and we cannot get anything out of this pixel level thing, because it's a limited knowledge. It will be just one value between 0 to 255. So we cannot match anything using this pixel. So we'll go a little bit in the higher direction, and we'll break the images into the small squares. Okay, so since this breaking the images into pixels is not of any use, because of it's not of any use because of the amount of the low amount of information that it contains. We will break the images into four, not four, like, no, it's written, it's broken here into 6 pieces, but we can break the images into how many pieces as we want. Okay, give me a second. Okay. No, give 1 second. I'll come back into. Okay, so what we did is that we broke down the words, broke down the images into smaller chunks of like this. If you can see, there is nose, there is eye, there is mouth, and from the cycle we have like seeds and wheel, and from the violin and all these things. Then what we do is that then what we do is that then we sort of, yeah, sorry, then we sort of plot histogram of that. Like if we see here, so let's say we break down the break a lot of images into smaller chunks, and we counted how many cycles, seats that we have, or how many cheeks that we have, or how many eyes that we have, and we plot the histograms accordingly. Okay. uh, uh, So each images now is represented by a vector z, where k is the size of the code book. So now you can say that. So let's say, and so all the unique things are now put together. Okay, and like let's say there is a eye, it will be the two eyes will be merged and to make one eye, and all the unique things are put together, and let's say that the size of the Unix set is k. We say that the size of the code book is k, and the image is represented by a vector of z, that has like there's like k length. And then we what we do is that then we sort of so initially all the values of this vector will be 0, and then what you do is that then we count the number of and certain element in an image, then we increase that value to that level. Let's say we have a code book, and now we are sort of looking at this image, and we can say that there is a I here, so that's why I'll just increase the value of the value in the vector that corresponds to the I, and so on. So it's like one not encoding, but like we're increasing the value. Then the each element zi equals to wi into ni, where wi is the fixed weight for visual word, and the ni is the number of occurrences of this word in the image. So as I was saying, so and each of the codebook element are given a weight. So let's say let's say we have an image of a person now. It lies the first image, and what we'll do is that we will take the I. Let's say we're giving a score to the patch that contains the I. So what we'll do is that we'll go to the code book, and we'll go to the value that correspond to the I patch in the code book vector, representation vector, and then we'll set the values to equals set the value to the weight corresponding to the I patch times the number of occurrences of that eye patch in the image. Since there it's an image of a person, so I guess that will be 2, and if the weight is, let's say, 0.75, it will be 2 times 0.75, which will be around 1.5. Okay, so and we have a vector where the eye patch correspond to value correspond to the vector where the value correspond to the eye patch is 1.5. Similarly, you can do the same for the nose and the mouth and everything. And given a set of n images, so if now we have n images, now we'll get a matrix. So since each vector is a size of k, and we're getting n of that, it will be k cross n. The matrix size will be k cross n, and the query image q, we need a vector similarity. So let's say like we have a query image, and we need to find that this query image is similar to which of the images in this entire matrix. So what we do is that we take the query image and we take the entire vector z matrix, and then we get a score, and then we sort the score by descending order. Okay, and so we use L2 normalization, that is equivalent to measuring the equivalent distance between the vector z and q. Okay, and what we do is that after getting the scores for all of them, what we do is that what we do is that we say that this image is corresponding to this image, because in the big Z, the capital Z, we had small z's, like the vectors. And if an image is corresponds to a vector in the code book, so not in the code book, a vector in this capital G, we assign that image as that image as the target image. Okay, so let's say for an example, so bag of words is used for image retrieval. Okay, so since you see this is an image of some university, Oxford, I guess, maybe, and this is the same university taken from the top view, and this is the same university taken from the front view, and there's a lady standing here. And what we did is that, so this is the query image, and this is the these are all the, so this is the 19th image in the corpus, and this is the 15th image in the corpus. So what we did is that we created vector out of this. So we created vector out of this. Let me draw. Use view. There is no way to draw here, I guess. There is no way I can draw here. Yeah, so there is no way I can draw here, but just follow my mouse point here. What I'm saying is that so here is the uh, image of this beautiful campus, and so there are like, let's say, hundreds of images that are like lined up here, and we got the vector. But this query image is matched with this image and this image only. This says that our image so this says that our image is uh this says that these two are the retrieved image from the image corpus that is equivalent to this image, our query image, just by comparing the bag of words of this image with this image. Okay, then you can use the bag of words model for the classification as well, such as like let's say each image now is represented by z, and gi is the number of occurrences visual word ci in the image. You know that, as I said, each image will be represented by a vector g, and each element in the vector will represent a visual word, and we will as will the value of that corresponding visual word will be the weight of that visual word times the number of occurrences of that visual word in the image. So, that's how we got C. And so what we do is that then you can choose some machine learning algorithms such as naive Bayes. And so what naive Bayes does is that it chooses the maximum posterior probability of the class C given image Z, assuming features are independent, and that means linear classifiers with parameter estimated by visual word statistic on training set. So then support vector machines. We can take two images G1 and G2, compare using a kernel function like phi, and um, and this is again a linear classifier for us. So what we're doing is that we're using these features as an input to our classifier, like naive Bayes and support vector machine, to use it as a classifier. To use it as a catalyst for the classification problem. So then coming to the final thing. So this is the same thing, but uh, I just put it out here like this is an image. So this is like image 1 up to image n. So then we're sort of computing the descriptors of the image by vectors, yeah, and we're using that vector to do the histograms and to find the clusters and frequencies, and we're using that to compute the distance matrix. And the distance, if the distance between two images are smaller, we can say that these two images belong to a class, and we use that information to the classification machine such as SVM to classify our target image. Okay, so this was all about yeah, this is all about the what we need to know about this feature matching, and using different techniques such as bag of words and VLAD to use this feature matching for different instances, and how we can evolve from feature matching to sort of classify images using our using our uh, using our algorithms and by our classical machine learning algorithms. So now, after this point, we'll be running the codes for some time. Then we'll close the session. But before that, I'd like to take like a short 5 to 10 minutes of break, just bathroom breaks and all. We'll meet again after 10 minutes. Thank you. Okay, so we'll go into the code now and see what is happening there. Okay, so let's just open this in Colab.
Okay. So this is the lecture one code, and yeah, so I think I made it bigger last time. Okay. Yeah. So starting with the code, we'll first in this code we'll sorry. Yeah, what we'll do is that we'll do regression with ransack for robust curve fitting. So if you could recall in our session, we first started to solve the problem of feature matching using regression, where the two features, uh, two identical features from the image would be plotted, and that plot will be used. Yeah, that plot is used to fit a curve in the plot. And at first, we saw that we assumed that um, these uh, points in the transformed image is a operation of translation or rotation or a combination of them. So what we did is that we tried to solve this matrix operation by using solve this matrix operation using regression, and then we saw that there's a problem of our uh, yeah. So we saw that there's a problem of um, we saw that there's a problem of outliers here, where at the outlier influence the final curve, or the final regression line that we're trying to learn. And to solve that problem, we then sort of try to uh, yeah, use the ransack algorithm. Where in the ransack algorithm, we pick two random points, then we draw a line to connect to those 2 points. Then we sort of define a neighborhood around that line, and we count the number of points that comes inside that neighborhood. And the more number of points that comes inside the neighborhood, the more is the score. And then at the last, we'll do this um, iteratively, and we always store the best line uh, by storing their parameters and as well as the best score corresponding to that line. In that way, if we do it, do this iteration a few number of times with a fixed number of epochs, we will come across a line which will be the best, and it will ignore all the outliers that is there. So we discussed that here in our live nodes, and we saw that S3 and theta 3 are the two best sort of lines. So to do that, let's just run some code now. Yeah, so let me just connect to the GPU first. Okay, it is connected, and so you can see these are the libraries that we're using, and these libraries were pretty simple. The first one is NumPy. NumPy is used as a Python matrix multiplication and matrix operation library, where what we can do is that using NumPy we can define NumPy matrix, and we can use that matrix to sort of represent our data and do all the matrix operation with it. The second library is pandas, and the pandas second library is the pandas, so the pandas are like the library. We use them while dealing with the data. And the third one is the matplotlib library, which we used for plotting curves and plotting charts and yeah, charts basically. And the scikit-learn library is a library that we will use to uh, scikit-learn is basically a machine learning based library that has a lot of machine learning algorithm as well as errors and many things that related to machine learning, and we will be using them for the mean square error and sample without replacement. If you go to the branch algorithm, you can see that there's a provision of score. Okay, so the score function use mean square algorithm, and this first line draw n samples h that belongs to x at random. So uh, so this uh, uh, this hypothesis drawing of n samples without replacement is provided by this particular function, sample without replacement. Okay, so we'll just run that. Great. Then coming to this regression part, so there is a class that is written for regression, but you can use scikit-learn library for that as well. But since we're doing it for the first time, it is better to always code that up. So there is order. So the order of polynomial that we are solving, that we will be solving, and then there is bias. Bias is a bias is the bias term that we have for our regression. So we define all these variables first, and then we define all those functions that we need to that we'll need for our uh, regression problem. So one is predict. So prediction would be yeah. So let's say we have a line that is fitted on our data. So what we can do is that we can just then pass any variable x uh, to that, and we can get the corresponding y because we have the line. And here they are using curved line, for example. So what you can say that yeah. So what you can say that this curved line is but you can say that the predict function can actually give us this polynomial values, the value of y given an x, so this is the predict function. So then we have a solve function. So so the solve function contains all the things that we need to solve the equation. So let's just see. So first is initialize variables, then and then the first is initializing variable, then so best fit x and best fit y. So we're sort of storing this best fit x and best fit y in the algorithm. So this is best error and best coordinates and best fit x, best fit y, maximum iteration and threshold. The threshold that we use to set the neighboring line where we will count the number of points. So we'll initialize the coordinate array for us first. Then we'll do the loop. So this is the loop iteration that we will code now. This repeat block.
So what we need is that what we need is that so while the number of iteration is less than the maximum iteration, what we will do is that we will sample first step is sample without replacement, and it should be the length of x, the data set that we have, and we put the random set as seed so that it do not change iteration to iteration. And n here is the number of data set per iteration. So is the number of points that we are sort of uh, sampling out of the data set to uh, uh, like to data set to sort of put it uh, yeah, so sampling out of the data set to put it on to do the evaluation. Okay, then we'll find the coefficient for this model. So the coefficient are beta and yeah, the coefficient is the beta, and we'll use this data to do a polynomial fitting, not a linear fitting, to get the beta. Uh, then what we do is that then we will find the equation for the model and the errors. So we'll predict the we'll predict the value of the x with the uh, 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 with the model, and we'll get the errors. Then we'll find the coordinate of the point which has error less than the threshold. Okay, and we'll also find the linear points as well. So if the number of linear points are greater than the greater, we will keep that. Otherwise, we will yeah. So then we'll find the mean square in the new and old model. If the error for the current model is less than the and have more points inside the threshold, yeah, so if the number of points inside the neighborhood is more and also the error is less, we'll update the model parameters. We'll set that the best score. Now the close points is the number of points that is inside the close boundary of the neighborhood. We'll update the close point. We'll update the best error, and we'll also update the best coordinate, and also best x and best y. And then we'll also update the maximum iteration as well. And once this is done, so once this is done, what we can do is that, and we can do this for maximum number of iteration, we will find the best coefficients and the best score and everything out of best. So this is a function to visualize the same thing that we have done now. So let me just run it. Yeah, it is done. So now let's just load up a data that is uh, uh, hosted here in a CSV, and then find the ransack model with it and solve for it. So then, and once you get the ransack output for it, we will once you get the ransack output for it, we'll plot the same thing, and we'll get with the coefficient and all, we'll get the plot very nice. So let me just plot it. Yeah, so you can see this is a non-linear ransack estimated curve. So this is the inliners. Inliners means those are inside the neighborhood, and X marked things are outliers, or the things which that are not in the neighborhood of this predicted ransack line. And once you do that, once you get this, we can use this curve. So suppose let's say we have a point here in the X, we want to find the corresponding point in the image 2. We can just take the value of this point in the corresponding y-axis and get the point. So this is the code that is provided for the lecture here, uh, and you can get this code, and you can run it, and you can make it make yourself see how this code. So I didn't go to the nitty-gritty details of the code that was written there. So just the overall idea, like we set a maximum number of iteration, then we set the best score, error, and x coordinate, y coordinate, and everything. Then we run the algorithm to find to sample randomly and do the same thing over and over again for different sampling, and we will store the maximum, the best score that we have got, and we can then use that to draw the line that best approximate the intercorrelation point between the image one and the target image. So with this code is done, and I guess this is all the things that I wanted to cover in this session. The session is a bit short because the content that I had in the slide and the content that I wish to write in the board are done. But you so I'm happy to like explain it more. But since there are no students today, we will not be staying around. We will be closing this session now, and if you have any more doubts regarding this, you can ping me. I'll happy to resolve that in the discussion forum or in the next session. So for today, I think we will close it now and see you guys in the next week. Thank you.